Hey students, hope you're doing well today. Just going to walk you through a couple of example problems with optimization. So you started on this last Friday. You did a couple of them. Those of you that did get that done on time, thank you, by the way, for those of you that have been staying on top of the assignments. So I looked at what you submitted to me over the weekend and put up an answer key as well that you should have looked at. Great job with those. Those are two kind of classic optimization problems. So we'll certainly be doing more of those. But I want to show you a couple more today. Basically, the challenge with the optimization standard is that there are so many different scenarios that require you to have a broad understanding of just situations and then how to set up the function. That's really the challenge with these, not the calculus. The challenge is how to set up the problems. So the goal is just to give you a lot of exposure to different types, have you try a bunch of types, work through, do problem solving. So we'll be on this for a few days for sure. So what I'm going to look at right now is number 322 out of your online textbook. I'd encourage you to pause this, take a quick look at what that question says. And then come back to this. But anyways, they give you this picture. These are both some kind of telephone poles, and then these are wires connecting to the ground, and they're connecting in the same place. And the problem is asking for you to minimize the length of wires that you need to connect down. So we have to make the assumption that these are right triangles in this case to make this work. We know that these are 30 feet apart. I think it's feet is what we're dealing with. And then basically the X we're looking for is how far away do we want to put that stake in the ground so that this wire and this wire, if we add up their total length, is the smallest. So what ends up being needed in this case is an understanding of the Pythagorean theorem. That's going to form the basis of our function. So for now, I'm just going to call this length y and this length z. And basically, we want to understand a total length function, and it'll be eventually in terms of x, but our length is basically whatever the y plus the z length is, right? So once we knew that, we'd have our function. But we don't want extra variables, we just want an x variable. So how do we put y and z in terms of x? And so that's where the Pythagorean theorem comes up into play here. For this triangle over here, it's just a matter of x squared plus 10 squared equals y squared, and basically coming up with y equals the square root of x squared plus 100. Okay, so for that part, we'd be able to take out the y and put in square root of x squared plus 100. And then for the z, this one, you might be saying, well, we don't know what that side length of the triangle is. And you're right, we don't, but we do know that it's 30 minus x. Whatever x is, this is just 30 minus x. So we can do a similar thing, 30 minus x squared plus 20 squared equals z squared. So now we got z as the square root of all of that. And we can do a little, multiplying out here. So if I take this binomial squared, I get 900 minus 60x plus x squared, and then plus 20 squared, which is 400. So that whole thing is the square root of x squared minus 60x plus 1300. So that can go in for z, and we now have a function that represents the distance or the total length of those wires, and the problem says we want to minimize that. What is the length of x that minimizes this function? Now here's where I have a little bit of that's the hard part, by the way. I feel like in all these optimization problems, coming up with that is the most challenging part. If you can get good at that, you will be good at these optimization problems. But that takes a lot of knowledge of a lot of different things, and some creativity sometimes. But at this point, my challenge has always been, now that we have technology like Desmos, if you type that into Desmos, you can click on the minimum value that Desmos displays. I would encourage you to do this, by the way. Click on that minimum value and very quickly identify the minimum length is when X is 10. You'll see that in Desmos, very easy to find. But what we're trying to teach you in calculus is that, well, we can find those critical points, we can find that minimum value by taking the derivative of this function and then setting that derivative equal to 0 to find that critical point. That's what we learned last standard. We're trying to implement that in realistic situations, okay? But whereas Desmos took us about 2 or 3 minutes to type that in and then click on that to get this answer, I just worked this out, okay? And from here on down, I don't know if you can see, this was all my derivative work, okay? So basically finding the derivative of that required some chain rule work there. I don't know if you can see that. Okay, required some chain rule. And then I set it equal to 0, and I had some nice square roots in the denominator. I subtracted one of those terms over. I squared both sides. Lots of algebra to get to a quadratic function where I set one side equal to 0. I could then factor it and finally solve it to get 10. Okay, so we need to understand the calculus, right? That there's value in that, but it's hard to justify a lot of the algebra when Desmos makes it so fast. So we'll get to that. I'll try and make clear. I probably won't expect you to do one like this on the assessment, but I will expect you to show, certainly for some problems, how you would do this. Okay? So that's the first example. I also wanted to do one other one with you. So this is actually example 4.34 from section 4.7 in your online textbook. So again, read through it so you know what we're talking about here. But I believe it's basically saying there's an island and a shore. This is the island, this is the shore. It is 2 miles offshore and 6 miles to the west is someone staying in a cabin, and they're going to try and go from their cabin to the island, and they want to get there the fastest way. They can run 8 miles an hour, and they can swim 3 miles an hour. Okay, I'm sure Carter and Skylar, right? They're going to be our two students that are going to excel in this problem because they would beat us all swimming, right? I would die. I would drown about right there as I try and swim across. Wouldn't even get close. But Skylar and Carter, I'm sure you'd dominate that. So anyways, the question is, how far in these 6 miles should you run, and then where should you jump into the water and swim, right? Is it good to run the whole 6 miles here and then swim the 2 miles, or is it better to swim the whole way, or is there some sweet spot right in the middle somewhere, maybe X units across, X miles down, that then if you jumped in the water and swam, you know, this Y distance, that somehow makes it faster, okay? So lots going on here, but this is, again, a pretty classic optimization problem. So let me give you these thoughts. First of all, we want to remember we're trying to come up with a time function. It's always good to keep in mind what we're doing, and we want time. It's not minimizing distance here, all right? If it was minimizing distance, we would just go straight across the water the whole way, right? So time is what we want. So remember, distance equals rate times time. And since we want time, I'm going to divide both sides by r, and I'm going to think distance over rate is equal to time. So if we look at this first distance x here, so that's on land, so that's obviously their running speed. So to cover that x distance, the time for that would be x over 8. Okay? X distance over rate of 8 miles per hour will give you the time it takes to go from the house to that magical point partway down the shore. Okay? Then the second one, y, we want it in terms of x. We don't want another variable in there that's going to mess us up. So here I can do, what's this distance here if I know the whole thing is 6 and this is x? Well, that's 6 minus x. And so we have another situation here that's basically like the Pythagorean theorem from last time. That distance y is essentially the square root of 6 minus x squared plus 2 squared. Right? So that's our distance, the square root of 6 minus x squared plus 4 all over the time, or sorry, the rate, which is 3 miles per hour. Okay? So all that represents our function. So again, I feel like that's the hard part. It takes a lot of practice to begin to see and develop these functions. Okay, so that's why I wanted to show you some of this tonight. At this point, again, the derivative becomes kind of challenging. Here was my work for that one. Okay, so I'm not going to go through this as much, and I actually didn't even finish this one yet. I just stopped there. But you can see the process to go about doing that by hand. Makes it a little challenging, but type this into Canvas, not Canvas, Desmos. Find that lowest value, that minimum that we're looking for, and you got your answer. Okay, I know the online book actually goes through the answer, so take a look at that as well. Try and understand parts of that. And good luck on your homework today. I'm going to have you do a couple more problems from the textbook and then email me a picture. Soon after that, I'll probably have on there that you can start some Newton Alta ones. I am looking for you to do some Newton Alta to start with, and then email me or contact me with what ones you want me to go over in more detail, and then I'd make another video on that. But basically, these next few days, we're just going to be hammering through a lot of those optimization problems. So they're not going to be easy. You're probably going to get stumped. Get in the habit of trying it. If you get stumped, leave it. Don't give up right away. Come back to it later. Try some things. Email me and say, hey, Mr. Cundy, I tried this. What do you think? You know, and let's try and work through that, because you're not going to get good at that if you just, oh, I didn't figure it out right away in the first 2 minutes of looking at it, so I'm just going to wait until Mr. Cundy shows me what it is. Okay, you're going to have to push through it a little bit more. So do your best with that. This video has already gotten too long, so I need to be done. We'll talk to you later.